Hello everyone, hope you're doing well. My name is Mahmoud Kiasari and welcome to the new chapter of electrical circuit. So at this chapter, like the previous one, we would like to talk about the DC circuits. As you all remember, we talked about the KVL, KCL, we talked a little bit about the network theorem like the Thévenin and Norton, and after that we tried to solve a couple of questions and try to see that what would happen if we do actually use them in the real world. So at this point, we are going to have the next session or the second session of our lab. It means that this part, we are going to again talk about all of those concepts, not from scratch, obviously, just for refreshing your mind, then do some kind of calculation. After that, we are going to do the simulation. And finally, we are going to have the small lab over here to make sure that everything that you learned so far is going to be acceptable and also applicable. So without further ado, let's talk about it. As I just mentioned, at this point, we are going to mastering the core circuit analysis under the real world constraints. It means that we are going to see that what would happen if you do have different kind of circuits with only using one single 15 DC volt source and also different kind of resistance sets, because these are the resistance that we do have in the lab, so we are going to use it. Our gear would be about the digital multimeter. As you just know, I do have the small multimeter, we are going to use it, the breadboard, the wires, and etc. So for the DC source, we are going to use the 15 volt. So the very first thing that we are going to talk about is about the divider circuit. As you guys know, there are two important divider circuits, the voltage divider and current divider. So at the first, we would like to see that again, how would they work, and we are going to use them in the real time. Then we are going to talk about the Kirchhoff's law. As you guys know, we do have two important Kirchhoff's law about the current. The very first one would be about the KVL. We do have it as KVL or Kirchhoff voltage law, and we do have it at KCL. I'm going to talk about them again, but I'm going to do some kind of the calculation simulation and finally the lab itself. And finally, I'm going to talk about the network theorem. As you guys remember, we talked a little bit about the network theorem, and also the important part would be about the Thévenin and Norton. We are going to touch them as well and see that what would happen if we are going to use them in the real world. So let's start with the fact that about the mastering the divider circuit. As you guys know, we do have the two important dividers. The very first one is about the voltage divider. For instance, VR1 equals the V total, or what a V total means that the V of source that we do have multiplied by R1 divided by R1 plus R2. And obviously VR2 would be something related to that, but with different resistance. On another hand, we do have the current divider. It means that IR1 equals to the I total, means that the current that goes from outside from the source, multiplied by R2, the one resistance that we don't like, divided by R1 plus R2. The only thing that would be different between the voltage divider and current divider would be about the resistance that we are using. So what are the objectives? The objectives are obvious. We are going to build and accurately measure the standard voltage and current divider. We are not only going to calculate them, we are going to simulate them, and obviously we are going to measure them to make sure that it is actually going to work. We are going to observe and quantify the practical effect of loading on a voltage divider's output. We would like to see to what would happen if we, rather than only one R2, we do have another resistance beside of that. We would like to see what would happen if we change the R2. What would happen to our voltage divider setting? And finally, we are going to compare the calculated predictions with the measured reality and identify the source of error. At the end of the day, we would like to see that what is the main reason that the number that we calculated is not going to be as the same as the number that we do have. Obviously, the deliverables would be about the data that you can have a table for yourself in order to measure the calculated value and measure the value, and you also going to have the error. And obviously at the end of the day, we are going to analyze that to see that the short paragraph would be enough to explain what is the primary source of errors, with a specific focus on the impact of the DMM loading. So let's start. Let's begin with building a 15 volt to 5 volt voltage divider. As you guys know, right now we do have different kind of resistances. So if you would like to make a voltage divider to divide the main voltage, which is going to be 15 volts, to one 5 volt and another one 10 volt, I can use the 1K and 10K. So how can we prove that? Easy. As you guys know, the V out is going to be V or Vs, or the source voltage, multiplied by R2 divided by R1 plus R2. So if I multiply 15 by 1000 divided by 2000 plus 1000, I do have the 5 volt itself. I can simply find the current, and I do have the voltage at R1 and R2. Then for the second part of the lab, we are going to design a divider for 2 volt and confronting component limitation. So what does it say? The question is like this. Imagine that you do have the 15 volts as your source voltage, and the question asks that what should be the construction or the combination of your two resistance in series if I would like to have the V out of 2 volts. At this point you would simply say that R2 and R1 at this point are unknown, so I can write it down that VR2, which is 2 volts, equals to R2 divided by R1 plus R2 multiplied by V. So my V is going to be what? 15 volts, and I do have the somehow a connection or relationship between R2 and R1. Since right now I do have one equation, two unknowns, I can find another one, but since the question at the beginning didn't ask anything, it didn't mention anything, I can just put the numbers. For instance, if you put R2 as 330 and R1 as 2K, you can see that somehow you would get the 2 volt itself. At some point the question would ask you to make sure the current that would go through the source is going to be limited. On this point, if we use another equation, so that was the first equation, and for instance the question says that the current that goes through your some kind of circuit shouldn't be bigger than 10 milliamp. So at this point we would say that okay, divided by R1 plus R2 should be less than 10 milliamp. And this is going to be somehow the relationship between equation and inequality, but it still is going to be helpful for you to make sure that your R1 and R2 are not, for example, 100 ohms and 200 ohms. They should be bigger than that. Why? At the end of the day, we have to make sure the amount of current we get from the source is not going to be that high, because high current means that high power and it's going to damage your source itself. So we are going to prove this part as well. Hello guys, as I just promised, at this point we are going to talk about the very first lab that we have. Obviously we did all of the calculations, we had the simulation itself. So at this point we would like to do it in practice and see that whenever we are talking about the voltage divider, is it going to work or not? As you guys know about the voltage divider, I should have a source, as I do have it on over here on the top right side, and I do have my beloved breadboard. And inside this breadboard, I do have a couple of different, as the question asked for, we do have the power, which is this would be connected. We do have the positive section and we do have the negative section. As you can see over here, is connected from the source itself, and I do have around 15 volt. Then I do have the connection of 1K, which is going to be this resistor in series with another resistor. Important thing that you guys have to know is that whenever we're talking about the breadboard, actually all of these ones or the columns in these rows are connected to each other, while these kind of are not connected to another column. And also we have to know the fact that these two guys are not connected to each other. On the other hand, when we're talking about the power trail, we should see that on the top side, we do have two rows. So the very first row is considered as a positive. As you can see, it is connected through the red is connected to my power source. You don't see it right now probably, but it is connected to my power source. Then I do have this blue guy, which is connected to negative side of the power source itself. It means that all of these guys, all of these spots in vertical side are connected to each other. In horizontal side are connected to each other. Another thing that you have to know is that at some points between these two sections, the middle rows, they are not connected to each other, but since we are not using that, we don't care. But just in case, whatever you're using also these points, make sure that you're using one jumper between here and here. A normal jumper like this would do it with the job, just like this one, and connect it from this point to this point, and you make sure that all of those are connected to each other. So right now I do have a question. The question asks to prove the voltage divider, or some kind of find the voltages for each of these resistors. As you can see, these two resistors are connected to each other through spots. We all know that all of these spots are connected to each other. Maybe I can show it to you a little bit more. So all of these spots are connected to each other. It means that I use this spot for my second resistor, and you use the left one or for the left resistor on the top side. So these two guys are connected to each other. The positive section should be connected to one of our resistors, and the negative section should be connected to another leg of resistor. So we do have everything that we need. And the question simply asks for a couple of things. The very first one is about the voltage. As we all know about the calculation, the V out, the V of this guy would be the resistance of this guy divided by the accumulation times the voltage of the source itself. So simply, we can just use the voltmeter. It doesn't matter. Again, the voltmeter that I'm using is going to be like this. As you can see, the positive and negative section are connected to two jumpers, and I'm going to connect these two to the legs of my each resistor to make sure that the voltage is going to be right. Since we are talking about the red one, is it the positive one and moves from here, so it means that the current goes from here to the end to here. I'm going to use this leg, the left leg, as a positive one, and I'm going to use the right leg as a negative one. So let's use the voltmeter in order to measure the voltage for the very first one. As we know, based on our calculation, the voltage of the first resistor, which is 1K, should be 5 volts. So I'm going to connect this one to the positive section and connect this guy to the negative section. So the only thing that I have to see right now is that as soon as I start up my voltage source, I should have the 5 volt or not. So I'm going to start it. And right now, as you can see, it is something around 5 volts, which is good. Then we have to, again, turn off the voltage source. Make sure that all the time you turn it off and then do everything that you would like to do with your circuit. Then we have to do the same thing with the second resistor. So if I do that with the second resistor, I should have a number around 10. So let's see what is happening over here. As you can see over this side, it is around, exactly it is 10. So the next question is another circuit, and actually, as you all know, based on the calculation and the simulation we did, we found out in order to get a 2 volts out of the second resistor, which would be this guy, we need 330 ohm, and we need the 2K itself. So again, we are going to prove the voltage divider, that whether it's working or not. So based on our assumption, if we do have this combination of 2K and 3 ohm, while we do have the voltage source of 15 volt, the voltage of this guy should be 2 volt or negative 2 volt. It's some kind of based on wherever you connected this one, it should be 2 volt, and if you connect it backward, it would be negative 2 volt. So let's do this. I do have the connection like this, then I do have another connection like this. So based on that, I can see that my voltage is around the 2 volt. So it makes sense. By considering the 2K and 303, based on the simulation and calculation, we found out our practical thing also works. Your source itself. So we are going to prove this part as well. And finally, for the lab number 1, part C, we are going to talk about the current divider and the reality of loading effects. So as you guys know, what a current divider means that I do have a source and I do have different resistors in parallel together. So the current divider at this point is going to be what? I do have a 2K, I do have 1.5 on 1K, and I do have a 10K itself. In order to find the current inside each branch, since I know that each resistor is connected in parallel with my source, all of the voltages are going to be 15. All of them are going to be 15. 15 divided by resistance, based on the Ohm's law, as we know, I is equals V divided by R, is going to give me the I1, I2, and I3. For finding the I total, the only thing that I have to do is either adding all of them, or I can find the R total. R total would be 1 over R total, divided is equals 1 over R1, plus 1 over R2, plus 1 over R3. So we would like to do the simulation and also the lab or practical thing to make sure that number that we get and is also going to be right, as well as then each number that we get for each branch. Another part of the question that we would have is demonstrating the loading effect. Imagine that you do have 1K and 1K and it's already connected to 15 volts. Since both of them are the same, means that my voltage is going to be divided in half. 7.5 volts over here, 7.5 volt would be over here, based on the logic or based on the formula. But what would happen if I make a 10K in parallel with 1K? So at this point, as you guys know, my kind of resistance would be a little bit different. It means that it's not 1K anymore. It's going to be around 900 ohms. So by putting the 900 ohms, at this case, my output voltage would be 7.14. What we are trying to show you guys at this point, we are trying to show you that if you use the voltmeter and the amount of resistance inside the voltmeter is not high enough, it's going to have some negative impact over your measurements. Most of the time when we are connecting the voltmeter, this voltmeter has the internal resistance of 1 mega ohm. So the combination of 1 mega ohm and 1 kilo ohm is going to be something around 1 kilo ohm. It's not going to have that much of effect. But imagine that we do have a case that my resistances are not going to be 1K and 1K, are going to be 500K and 500K. we expect to get a 7.5 again. But the problem is that the internal resistance of my some kind of voltmeter is going to be very close to 500k. So at the end of the day, the combination of these two guys is not going to be 500k anymore. It's going to be something around 300k. And as you guys know, if we reduce the amount of voltmeter resistance, we are going to have the less amount of voltage, so it's going to be problematic. So it is so important for us to know the very first thing about the amount of resistance that we do have inside the voltmeter, and also the fact that this guy should be in parallel with a very resistance in comparison to its. So at this point, based on the question that we already asked, we do have 3 resistors in parallel. So it could be a little bit confusing for you. Let me explain everything. So at this point, on the top right side, again, you can see I do have the sources. I do have the positive and negative. They are connected to some kind of voltage source. I'm not worried about it. Then, since I would like to expand my circuit a little bit more, instead of just connecting these 2 wires, which comes from the positive and negative of the source directly to the circuit itself, I would connect them to 2 spots at this point, if you can see on the left. Then I use 2 jumpers, and then I connect them to the main circuit itself. So let's talk about the main circuit. As the question asks, for the main circuit, I do have 3 resistors in parallel. One resistor, which on the left side, I know it as 2K, another one 5.1K, and finally I use 10K itself. So right now, we know that each of these spots are not connected to each other, but for parallel circuit, I need 2 common spots. What can I do? I can use the jumper. As you can see over here, the jumpers, for example, like this one is connecting the top side of the K to the top side of the 5.5K. Another jumper is connected to the top side of the 5.5K to 2K itself. And also I'm doing the same thing in the middle and for the bottom itself. And in the meantime, I'm going to connect the positive side of the 2K, which I know this guy, and they're connected to each other, to the positive side of the source, and the negative side of the source. So everything is settled, and let's answer the question. So question simply asks to find the current inside each branch, and finally try to prove that actually our some kind of KVL works. It means that the amount of current that I do get from the source itself is going to be as the same as the accumulation of I1 plus I2 plus I3. First of all, let's find how much current that goes through the main circuit. Again, turn everything off, and after that, you need to make sure that you are going to have the current section, or going to have the milliamp section for your ammeter, then try to connect it to the circuit. So it means that the only thing I have to do, just get rid of this guy and connect it to positive side, because I know current would go through there. This is going to directly connect it to source, and then I can connect this guy to the place that my red wire is supposed to be connected to. So I do have something like this. Right now, if I just turn this source on, make sure that before do any kind of modification to your system, turn everything off, especially when you're talking about the voltage source. So turn it on, and right now, based on the calculation, I should see a number around 11.9. So as you can see over here, my number is around 11.8 milliamp, which is pretty close. Then I have to turn it off, and after that, I know my total current is this much. Then I have to connect everything over here, and I do have the connection over here. So I do have my total current, and everything is fine. So the only thing that remains to measure the current that goes inside this branch, this branch. You know, when you connect our ammeter, it should be in series. It should be in the way why it doesn't have any effect over the other side. So the only thing I have to do, for instance, if I talk about the 10K, I have to disconnect this part, and I have to disconnect this section. The current, instead of going this guy directly, first move through the ammeter, then go through that. So the only thing you have to do, disconnect this one, or you can disconnect this leg, or it doesn't matter at this point, because we know this one is, or this leg of the 10K is not connected to anything. So the only thing I have to do, connect the positive side, then I have to connect the negative side. Cool. So right now, everything is settled. The only thing I have to do is just turn the source on. So if you turn it on, based on the calculation and based on the voltage over based on other kind of thing or other ways that you have in your mind, it should be something around 1.5 milliamp. So you can see over here, if I turn it on, I do have 1.5 exactly milliamp. So it means that the currents that go through the final one, or the 10K, is right. By the way, make sure that when you are connecting this guy, especially, should be in the right spot, rather than that your circuit is going to be broken. So we have to do the same thing with the middle one. Let's do it. It means that either we can get rid of this connection,
or this connection, doesn't matter, then connect it directly to this guy. So if I do that, for instance, I disconnect this one, and I know for a fact this guy should be a positive. However, make sure that you're turned off the source. Then I have to connect the negative side to what? To this port. Okay, everything is settled. Let's measure the current. So this current should be something around 2.94. At this point, we do have the wrong number. As you can see, it's still negative 1.5. So we have to fix the issue. Let's just look at it, that how we can do it. What was the part that we did wrong? I mean, it's completely, if you have any issue with the circuit itself, let's just look at it. So at this point, you can see everything is connected beautifully. So right this part. So what we did, we some kind of disconnect this part and again connect it back to the section. But here's the main problem, because at this point, if I disconnect this part, the current also that I do have from this point, from this guy, is going to affect, or is going to affect this guy as well. So it would be better to what? It would be better to, rather than doing that, I can either find the voltage of this one or find the voltage of my resistor divided by the whatever resistor that I have, or I can check that what would happen if instead of disconnecting that, I would disconnect this guy. So if I do that, probably going to have another issue. Let's check it. So yeah, again, as you can see over here, I do have another issue that the current that I'm measuring at this point is around 4.47, because this current is going to be the accumulation of these two guys, of the one that goes through here and the one that goes through here. In order to solve this issue, because as based on the connection, I cannot find any way to measure this guy. I can find the current that goes through this one. Actually, the current that you're watching, or that the current you're trying to see, is the one that the accumulation of this current and this current. You can, since you do have the current over here and you know the KCL, subtract whatever current that goes through here by 4.5, and you can see that the answer is around 2.9. Let's just wait to see that that one is going to work as well or not. Instead of just working on the right side, we know that this top part is going to be accumulation for both of them. Let's focus on the bottom side. Let's see if that's going to solve the question or not. Again, disconnect this guy. By the way, make sure you turn off the source itself. And this kind of issues, it's so common. That's why instead of just focusing on the right answer, I'd rather to have this kind of issue by myself to make sure that you guys are completely understand it. So the one thing I'm going to do is that rather than disconnecting on the bottom section, then connect it to another wire, I'm going to disconnect this leg itself. Because obviously, as we know, the current moves through this leg, right? So I'm going to do what? Oh, yeah, this is disconnected. I'm going to connect this guy on its place. Then I'm going to connect this one to my positive side of the ammeter, as you can see like this. Then I'm going to connect this part, which is a negative side of my ammeter, to one of these wires. So if I do that like this, at this point probably the problem should be fixed. But if that doesn't fix the issue, that's totally fine. It is because of the connections that we have. Okay, like this. So at this point, I should have the right current. Let's see. I don't have any current at this point. This kind of, it doesn't make sense because the current moved through this point. Then the current goes that way. And when the current goes this way, oh, because of the fact that whenever you're doing that, you're actually going to disconnect everything. So I'm going to get rid of this and again move it back to the normal that it was. Everything is so inside each other right now. So let's have the solution and let's see how we can actually fix it. At this point, you can see that everything is connected very compact and to each other, and it doesn't matter if I choose this wire, or if I choose this wire, the current that I'm going to have is not going to be the right one. At this point, I'm going to use the third jumper and I'm going to disconnect, for instance, this guy, right? If I do that and if I use the jumper between, it means that instead of just disconnecting any of these two and have effect over the whole system, I'm going to get another spot in the between while both of these guys are connected to each other, and then I'm going to measure the current. At this point, the final answer should be right. Let's see what would happen. Okay, cool. Perfect. That is completely right. So as you can see over here, our final answer, it is 2.98, which is somehow very close to the number that we're looking for. So I considered some kind of problems that you could have when you're dealing with this kind of circuits, especially when we're talking about this and this guy. It means that rather than using the way that I told you, using the third jumper, we are going to disconnect this guy, or we're going to disconnect that guy, or we're going to disconnect that guy. Any of these ways is going to have effect over the system. Why? Because we do have another guy and at the last, and this one is going to have effect over the system. In order to solve this kind of case, while you do have other kind of components on your right side, it would be better to use the third jumper, and instead of disconnect these two, just connect it over here, and on that end, put your ammeter in between the wire, sometimes node, and after that, the leg of your resistor. Obviously, you guys know how we can do it with the next one. So the answer with the first one is around 7.5 milliamp. So it doesn't matter if I do it or not, but again, we have to do based on the third jumper. So be very, very careful about that.